Swayam Prabha. Digital India. Educated India.
Okay, so once again let us continue with the topic on shear strength, where I have stopped in the last lecture. It was basically I am just revising the mechanics part of it before going to shear strength of soil. And at a point inside the soil at any depth, I can imagine the state of stress, that what are the different component of stress are there that I have shown initially, and then I have considered the biaxial condition, that means only two normal stress and two shear component, and that of course is easy to find out, because in a particular known direction, generally in a vertical direction and perpendicular to the vertical, that other direction I can find out by applying whatever knowledge we have. Now, in fact, in the mechanics also, when there is a beam and suppose I want to find out normal stress in this direction or normal stress in this direction, by applying mechanics I can find out. Similarly, what is the shear at this and what is shear at this plane, that also I can find out by applying the mechanics theory whatever we have learned. Similar to that, suppose in the soil, if state of stress is known at a particular point, and but that is not the plane which is critical, there may be some plane where it will have maximum stresses. So, we have to find out those plane where actually a particular stress is occurring. So, sometimes we know the maximum, but where it is acting, that we have to find out. So, because of that we have taken a generalized biaxial problem and element, and with generalized state of stress, and then I have imagined one plane which is inclined theta with the original plane, and with that inclined plane, what is the normal stress, what is the shear stress, actually suppose we have to find out. And for that, what we have done, we have suppose let us take now. So, this is the one, it was this is the plane was there. So, what I have done previously, I have on this plane. So, on this plane actually there is a normal stress. So, normal stress into the area of this is the A. So, this area of this will be A cos theta. Similarly, it will be A sin theta. So, I have what I have done, I have this area multiplied by normal. You can see sigma x A n cos theta. So, that is the normal force, and that normal force again taken component to this direction. So, then again another cos theta will come. Similarly, shear on this plane whatever is there multiplied by area, that will be shear force. So, tau x y A cos theta, and similarly here on this plane we have normal force, suppose sigma y, and sigma y A n sin theta, that become normal force, and again I have taken component towards this to get the force equilibrium. Similarly, on this plane there is a shear stress is the tau x y A sin theta. So, again that becomes shear force, this is shear force, this is shear force, this is shear force, this is shear force. There are force component, and those four components I will take along this. And what is force acting on this? I know that this area here is A n, and the force acting stress acting is sigma n. So, sigma n into A n, that become the force. So, this force and these four force components, that component can be taken towards this, and then finally summation of forces in that direction ultimately at that point will become 0, and based on that I have simplified and I have got this equation, that is sigma n equal to this. Similarly, what is the shear force at this? I know area is A n, and if I multiply it by shear force acting on this plane tau x y, then that is shear force, and here also number of shear forces I have got, those also I have taken component in that direction, and then we have equated and then we have got the equilibrium. From the equilibrium we have got something equation, and then we have simplified and then used trigonometrical modification. By that you have got a expression tau n equal to this. So, these two are actually most important. That means, I know the stress condition at this direction and this direction, this is known and this is known, but I want to find out on any plane which is inclined by theta. Here suppose on this plane what is the stress. So, by these two equation, that means if you know the theta and if you know the sigma x and sigma y, I can find these two. Now, after finding these two, sometimes it is not enough, find out the maximum value. I need to find out at which direction this maximum is occurring. To find out that, particularly this, to find out the maximum, I can differentiate this and equate to 0, that is maximize I am doing, and based on that further simplifying I am getting the expression. That means, that theta, this is double angle 2 theta equal to this, then theta will be half of that. That means, if the theta value is tan inverse half tan inverse half of this half tan inverse this, if the value of theta, on that plane we will have either maximum or minimum. So, both can be there. So, from this equation I can get. Now, this equation, by using equation again and again, sometime it may be tedious. So, in soil mechanics, particularly even in the mechanics, instead of using this equation, sometime we use a method called Mohr circle method. And what is a Mohr circle actually? It is a circle actually. Now, the sigma n and tau n with the variation of theta, suppose at this point I will make a plane along this, I make a plane along this, I make a plane along this, the different orientation I am changing, and because of that, on that I am getting a sigma and tau. Those points actually, locus of those points, if we follow, then we will see that they are following a circular path. So, that means that is actually circle. So, using that circle, sometime we will be able to find out different things of what is maximum, what is minimum, what is the maximum shear, what is the maximum normal, what is the direction, or if we want to find out at a particular orientation, what is the shear, what is the normal, all those things we will be able to find out. So, how to find out that Mohr circle? First I will explain that, and then use of Mohr circle in a further detail I will discuss. So, you can see here Mohr circle of stress. The expression for the normal and shear stress can be represented graphically by a useful device known as Mohr circle of stress. It can be shown that locus of state of stress at any point is a circle. That what I have shown, this point I take this direction, now I take this direction, now I take this direction, different direction I am orienting the plane, and then I am finding out the sigma x and sigma tau x. Then that can be shown that. So, whatever expression I have shown previously, we can square them and then add and simplify, then we can get a expression like this, an expression like this. And this expression, if you look properly, then you can see it will be sigma minus suppose r plus suppose tau square equal to, if I say r square, or sigma minus a suppose. So, like that means, this is a equation of circle, and this is this a0 is the center of the circle, and this under root this will be the radius of the circle. So, we now by observing the expression of normal and shear, we have squared and added and finally rearranged, and what we have got? We have got an expression, and the next expression is nothing but an equation of a circle. And if you have the equation of circle, that circle will have a definite center and radius. So, that is what is the radius actually? radius is this, and sorry, center is this, that is one coordinate is this and another coordinate is 0, and this is the radius. So, we will show this in the next slide. You can see the expression is an equation of a circle with center at sigma x plus sigma y by 2 and 0. So, this is x coordinate and 0. So, that means, if this is 1, so what is the center? Sigma x plus sigma y by 2 and 0, that means on this axis only, the center will be on this axis. And what is this distance? This is actually sigma x plus sigma y by 2. Okay. And now, the center, now with this center and this become the radius. So, I can draw a circle now. So, this is actually Mohr circle, that whatever each point actually giving you tau and sigma represent different planes. So, this is a plane, this is a plane, this is a plane, suppose this is a plane, like that. So, all different plane actually giving you tau and sigma. So, this Mohr circle can be utilized very effectively to find out the stress at different direction. Now, we can see how to draw the Mohr circle, steps in construction of Mohr circle. So, this is the state of stress. You can see now, this is x direction and this is y direction, that there is a sigma x, there is a sigma y, and there is a tau x y, and this is a if this is tau x y, then this will be tau y x, and there will be this should be an equilibrium. So, this and this will be opposed, this and this will be opposed, and biaxial condition we can show that this tau x y and tau x y x is same. So, ultimately, we can write without any suffix actually here. And so, now the normal stresses are plotted as horizontal coordinates, normal stress. So, this if I consider this, so this direction will be normal, and tensile stresses are considered positive in general, and that means it will be in this direction, and compressive will be negative in this direction, but in soil mechanics we take compressive as positive. So, that means when there is a compressive force we will take in this direction. And so, now we will see there is a plane, there is a p plane, there is a q plane, there is a r plane, and there is a s plane. There are 4 planes are there, and I can show you that p and q, p and r will represent only one point in the circle. Similarly, q and s plane will represent one point in the circle, and they are in the opposite direction, that I will show you in the next slide. And I have to follow some sign convention actually, as I have mentioned that tensile stress is positive and compressive is negative in general in mechanics, but in soil mechanics, since compressive force is most important because comes there. So, compressive is taken positive and tensile is taken negative. Similarly, shear also, what shear will be positive, what shear will be sometime directing sometime there is a plane, sometimes shear may be this, sometimes shear may be this, which one is positive, which one is negative. So, this is the sign convention. If this is the body and shear direction right face downward, that is positive. The shear stress are plotted as vertical coordinate, that means like normal stress I have shown this direction. So, shear stress in this direction, and positive shear stresses are plotted above the origin and the negative shear stresses are plotted below the negative. So, plus this side minus this side, and again on the when the state of stress shown on element. So, based on this, how what will be taken positive and what will be taken as negative. So, this is the one. So, right face downward or left face upward, both are positive. Similarly, right face upward and left face downward, that is negative. So, this is the sign convention to be used to draw the Mohr circle. So, now I can show you that this is a Mohr circle, this is sigma direction and this is tau direction. A number of things can be shown here. You can see the positive angles on the circle are obtained when the measured in the counterclockwise sense. That is also another important thing. When the plane is rotating counterclockwise, that theta is taken as positive, and if it is in the clockwise direction, that theta will be taken as negative. And an angle of 2 theta on the circle, that means you can see here that is shown 2 theta, an actual element it will be theta. So, when I will draw the Mohr circle, on the circle when I will see the it is rotated by 2 theta, actually on the element rotation will be theta. So, that is double angle, all expression I have shown that. So, that is one important point to be noted. An angle of 2 theta on the circle correspond to an angle theta on the element. And you can see Mohr circle for the assumed stress at the stress point, assuming sigma x is the sigma x was the bigger one than the sigma y. So, based on that we consider major and minor, there will be and then 0. So, both sigma x and sigma x value are there in the plane element, and they are greater than 0, but sigma is again greater than sigma y. The normal and shear stress on the vertical plane P give the coordinate one point on the circle. So, that means this is the P, suppose this is the point P. This is what actually directly, if this element is there and this is a normal and this is shear, suppose this is shear, this value, this is suppose 100 and this is suppose 20. So, 100 comma 20, this is a coordinate. Okay. So, that suppose point P I have got. So, right side face of the element represent this point D. Now, the plane R, that means this is suppose P and this is suppose Q and this is another plane R. So, this plane R vertical and 180 degree from P, that means this plane is 90 degrees and this plane will be 180 degrees, that means it is rotated by 180 degrees. So, once it is in the circle, it has to be rotated twice. When element it is rotated by 180 degrees, on the circle it will be double of that, that is 360 degrees. So, that means this point, if we rotate this point, so R face whatever value is there, that will be rotated 360 degrees, that means it will starting from here the rotated 3, that means coming back to this point. So, that means the plane R also vertical and 180 degree from P is located at 2 theta, that means 360 degrees on the circle from P, resulting in the same point of the circle. That means P and R will be in the same point, that indicating D. Similarly, the stresses on the horizontal plane Q and S plot a different single point E. Suppose now I will read this point. So, suppose there is a shear here and there is a normal here. So, that value again give you another coordinate, that coordinate suppose if this is positive, this will be negative actually. So, it will come somewhere other side, suppose point E is coming here. So, suppose I read this face, then I will get this point, and when I will read other face, this one, this is again at 180 degrees from this plane. So, that means in the circle it will be rotated by 360 degrees, then again it will after rotating it will come back to this point. So, that means this face and this face will be representing this point. So, this face and this face representing this point and this point. So, this point now we are getting 2 points we are getting on the these two are on the circle actually. So, and they are in opposite direction of the circle. So, these 2 points if I join and intersecting the normal axis, that actually it will give you intersecting at a point that will be the center of the circle. Okay. So, next slide I can show you that, and this shows that the stresses on parallel planes of an element oriented at an angle are correspondingly equal. The point of intersection of the line D connecting these 2 points, connecting these 2 points, that means D and E, connecting these 2 points, and the horizontal axis sigma n gives the location of the center of the circle. So, this and this if I join and I get location of the center of the circle. The diameter of the circle is d. So, these two are actually opposite direction of the circle. Now, further you can see and now by observing this you can see the maximum shear stress is apparent to be equal to the radius of the circle. So, you can see along this if I take a one point here, sorry, if I consider a point here, this point give you a sigma value equal to this much. If I take this as origin, this is the sigma value and this is actually tau value. So, that means the tau value is 0 here, because on this axis there is no shear value will be increasing when I will go from this axis to this towards this. So, at this point shear is 0. Now, if I move by rotating the plane, shear value is increasing along this. If I go like this, like this, like this, so it is reaching to a maximum value at this point, and then if I further rotate, again shear value will be decreasing, and again at some time it will be reaching to this value. So, this is, that means the maximum shear stress is possible which will be equal to actual radius of the circle. So, that is the thing, first thing is noted here, the maximum shear stress is apparent to be equal to the radius of the circle. The orientation of this stress with respect to the original plane can be either be measured or calculated with the help of trigonometry. That means, this which plane where actually this is happening. So, between normal direction, maximum normal direction and maximum shear direction is 90 degrees. That means, on the circle we are seeing 90 degrees, that means on the plane actually what should be, it will be half of that 45 degrees. That means, the plane on which the maximum normal stress occurs, that is the plane. You can see here at this point shear is 0, but normal stress you can see along whatever I have shown, that if I move along this, normal stress is increasing like this and again decreasing and coming to here. So, here actually if I move along this circle, the shear stress normal stress becoming maximum here, and if I rotate then it is coming minimum here, and then if I go this way again coming to this point. So, that means the maximum shear stress is normal stress is here and maximum shear stress is here, and when maximum shear stress is occurring, you can see normal stress is 0. The plane on which maximum shear stress occur, there actually your normal stress is 0. Similarly, the plane on which at this point no normal stress is not 0, normal stress is this, the value is this one, whatever value will read here normal stress, that is the normal stress value. Whereas, the point plane on which the maximum normal stress is occurring, this is the point, suppose this is the maximum value of shear stress, or this is the minimum value of maximum value of normal stress, minimum value of normal stress. At this point actually you can see, since on the x axis only there is no shear value, that means the plane on which the maximum normal stress is occurring, there actually no shear stress, that is actually on condition actually you are getting where. So, that is a check, that if you get maximum normal stress on that place, you will not have any shear stress, whereas the plane on which you are getting maximum normal shear stress, on that plane non necessarily the shear stress, there will be some shear stress value, there should be some normal stress value. What is that? The normal stress is actually you have to read this from starting from this, suppose this is the origin. So, starting from this we can read this value, that is the normal stress. So, now this orientation as we have shown by calculation, that sigma n, tau n and then tan 2 theta n, by that one can calculate what is the value and what is the orientation. So, by calculation, and but calculation I told that if I want to do many calculation, then it is tedious to do so many calculation, but if once you draw the circle I can find out everything graphically. So, that is the thing. So, either it can be done trigonometrically or by measuring the angle. So, if I this plane how much angle, suppose I can just measure the angle and this angle is in the circle, but actual element it will be half of that. The principal stresses sigma max and sigma minimum can likewise be spotted and determined easily, that way this and this, and orientation can easily be measured or calculated. Further, so orientation, so this is the original state of stress and the maximum happened here, that means it is rotated this direction. So, clockwise direction, that means negative angle. So, this is negative angle, and how much you measure the angle here, that is 2 theta. What is the value of theta? Half of that. So, furthermore, on the principal planes the shear stresses are 0. You can see the principal planes. So, principal planes, this is one principal plane, this is another principal plane. So, on that principal plane maximum principal stress is occurring and maximum principal stress occurring, where actually shear stress is 0. So, these are the important observation from the Mohr circle which can be noted. And you can see now, I have shown with this sketch, actually you can see this is actually suppose sigma 1, that is major principal stress. This is the direction of major principal stress, and then what is the major principal plane? That must be the major principal plane. So, this is the direction of major principal stress, but what is the plane? Plane is this, because normal stress is the perpendicular to a plane. So, if this is the normal stress, maximum normal stress, then major principal plane is this. Similarly, if this is the if this is sigma 3, that means minor principal stress, then what is the minor principal plane? So, this will be on this plane on which minor principal plane is acting. So, this is the minor principal plane, okay. And suppose on any angle theta, suppose this is the theta shown. So, I can rotate by this and I can find out other planes actually to find out the stresses. And a number of additional basic relationship which can be obtained from Mohr circle, that is actually you can see the maximum shear stress is equal to the radius of the circle, as I have shown here. This is the maximum shear stress, this is nothing but radius of the circle. Furthermore, the maximum shear stress are on plane that makes an angle 45 degree with the principal plane. So, if this is a principal plane and this is a plane on its maximum shear, this is angle 90 degrees. So, in the actual element it will be 45 degrees. The resultant stress on any plane has a magnitude of this, that means, and its angle of obliquity is equal to tan inverse this. Suppose if I take like this through this, at this point resultant, this is the resultant, this is the value of normal shear and this is the value of normal. So, resultant will be under root tau square by sigma square, and their angle, this angle will be tan inverse tau by sigma. And the maximum angle of obliquity is constructed by the line OT, that means you can see similar thing I have drawn here. You can see here this line from O, from point O, I can imagine number of line, one line I can dig here, this line actually I can change, and then finally it will become tangent at this point. Suppose at point T it becoming tangent. The tangent to the circle at point T, correspondingly the stresses normal and shear that correspond to the point T. So, that means at this point whatever normal, we can get the normal stress and shear stress at this point, I can find out stresses in the plane of maximum obliquity, that is the maximum obliquity, the angle of maximum obliquity, and at that point what is the shear stress, what is the normal stress, I can find out by drawing a tangent on the circle. It may be noted that shear stresses on this plane is less than tau max. So, tau max is here, but this is tau max here is less than this. That means, it may be further noted that slippage occurs at the point of maximum obliquity and not at the angle of at the angle where tau max occurs. So, if I join a line with tau max, which will be angle will be smaller than the angle of obliquity. So, that means, slippage will be occurring at maximum angle of obliquity, not on the plane where the maximum shear stress is occurring. So, that is the observation. So, using this I can utilize the Mohr circle to do so many several calculations, and that I will show you by showing some application, 1 or 2 application in the next module. With this I will stop here. Thank you.